Okay, great. Can you guys see my desktop?
Yes.
Okay.
I don't see the slide.
Yeah, do you see the slide now?
Yes. Yes.
Okay, just making sure it's not the presenter view, right? It's just the slide.
Yes. Yes.
Okay, great, thanks. Right, that's a large group. That's a large group of people meeting. It's larger than the Columbia lab meeting. Yeah. Thanks for the introduction, and thanks Professor Chua for inviting me. So I met Professor Chua at the Lehigh Robot Learning Workshop like 2 years ago, and she has kindly given me a very nice tour of the robotics lab. So I think Lehigh has a very thriving robotic community, and you guys really have a nice campus, which we don't have here in New York. And I'm excited to give a presentation today. Okay. So today I'm presenting the our IROS paper. And in this paper, we present a dynamic grasping system with reachability and motion awareness. Feel free to interrupt and ask any questions or give any feedback. Okay. So this work is in collaboration with Iradi, Shuran, and Peter. And Iradi is now a research scientist at NVIDIA. Shuran is an assistant professor, which is also my advisor. And Peter is a professor who just retired this year. So yeah, I would like to start with asking you guys a question. Do you think static grasping is a solved problem in robotics or not? Any thoughts?
Well, how do you define solved?
Like a solved problem, like we can, in any application, if we need to grab a static object, we can do that like fairly confident and precise.
So I think the current state of the art for static grasping is like for the beam picking tasks, right? So robots can already pick faster than human beings with high accuracy. But can you say this is solved? I'm really not sure, but it has certainly reached to a high level.
Yeah. Exactly. I think you're absolutely right. I think it really depends on like the type or even the texture of the object we are grasping, or the, like as you said, the setup of the task, right? Or like the input to the system, is it RGB or is it a mesh of the target object that we are trying to pick? And also the environment, is it cluttered? Is it cluttered in a bin or something like that? So yeah, but in general, like what we can say is for a static grasping task, we can achieve sometimes above 95% accuracy. And if you publish a paper on static grasping and you don't have an accuracy higher than 90%, then it's very likely that the reviewers will challenge this. So you really need to like justify that you have a hard static grasping environment setup. So, and for example, we have a group of analytical methods such as GraspIt that takes in a mesh, a representation of the object, and then optimize based on some predefined quality function like a force closure, form closure. And more recently, we have a group of machine learning based methods. For example, this work use RL to like clean up a cluttered group of objects. I think we can all agree on that the robotic manipulation becomes much harder in dynamic environments. And guess what? That's the cases in real world. For example, there are a lot of applications that require dynamic manipulation abilities, like human-robot handover or robot catching a ball, or dynamic grasping, etc. So that's why in this paper we study dynamic grasping, where the problem is to pick up a moving object whose motion is not known a priori while avoiding obstacles. And below is a video demonstration of our problem. And the target object moves along the red trajectory, surrounded by other object obstacles and also a top slab obstacle. And we will discuss how to achieve this. Right. So what are the challenges that appear in dynamic environments that does not exist in the static environment? Firstly, the continuous changes in the environment require online and fast motion or grasp replanning. This does not exist in the static environments because in a static case, we can afford more planning time because we only plan and then execute the plan. It's once and for all. And secondly, the motion understanding and prediction of dynamic objects become extremely important. We need to understand the motion of the objects so that we can predict the future pose, so that the robot arm can catch up with the target object. And then closed loop control becomes necessary. The system needs to consistently read from the feedback from the environment and then adapt its plan. Lastly, the approaching and closing motion of the grasp is non-trivial, and timing of those motions is important. For example, in a static environment, in general, if you plan a grasp and then if you have reached the grasp pose, the approach and close motion are trivial. In general, you just have a predefined or fixed close and approach motion. But when the object is actually moving, then this motion becomes non-trivial, and you really need a precise understanding of the motion to actually approach and closing the motion as the object moves. There are certainly, I see questions.
Yeah, this is Jeff,
yeah.
former office mate of Peter Allen, by the way.
Wow.
I wanted to ask you if dynamic motion or dynamic grasping includes, in your mind, situations where the grasp contacts cannot be, are not static, so that the contacts can move on the object. For example, if I don't know if you can see, but I'm manipulating a pen, this dynamic grasping, even if I do it slowly, do you include that in your thinking?
Not for this project, but I think that's definitely an interesting add-on. But I think it's more like into the in-hand manipulation task, where you manipulate a object in hand to rotate or.
That was the example, was in hand. Of course, it doesn't have to stay in my hand. I can do manipulations that involve contacts in other places in the environment that come and go, stick and slip, that kind of thing. Yeah.
Then I think in my opinion, I think it is a dynamic grasping problem, because you have to do replan all the time. Like you have to take into the change in the position or orientation of the object you are interacting with and keep doing the replanning. So I think it should be, yeah. Cool. So should I continue? Right. So yeah, so there are certainly a group of amazing prior work in the dynamic grasping, but they also generally make some assumptions along the way. For example, this prior work, it assumes only top-down grasp, and the target object slows down and comes to a stop before it's picked up. And this is another very awesome work, but it needs the human to signal the grasp execution, and the object has a relatively slow and small motion. Right, so here's another one. It's able to handle a faster moving object, but it does assume a known object motion. So in this project, we want to ask if we can relax some of the assumptions and still achieve a good performance. So our method consists of 3 components. The first component is a grasp planning component, and our grasp planning algorithm is both reachability-aware and motion-aware. And the second component is object motion modeling, and then our motion generation. So we will first talk in details about our grasp planning algorithm. So in our project, we use a database approach. So we pre-generate a database of 100 stable graphs for each object. And the generation of such a database is a 2-step process. In the first step, we use GraphSpeed to generate even larger database grasp. And then in the second step, for each graph generated in the first step, we simulate and execute those graphs in the Pipeline simulator with the physics simulation. And we have, for example, 50 trials for each grasp, and then we keep those graphs that has a high success rate, high enough success rate. We also add some noise to the position of the object so that our selected candidate grasp stable given some noise. So after we have a database of 100 stable graphs for each object, the grasp planning problem becomes at each time step, we need to pick a grasp from the 100 graph database. And here comes the trade-off. The trade-off between the size of the graph database versus the time to iterate through all graphs in real time. In general, the more graphs we have in the database, the more variety and the coverage we have in the approach directions. But at the same time, the time spent iterating all the graphs also increases with more graphs. So given our database of 100 graphs for each object, just iterating through all of them by simply checking reachability and computing IK is already infeasible in real time. So to be able to have a big database and also a real-time grasp planning algorithm, we borrowed the idea from our previous work. And in this work, we introduced the concept of reachability. And the intuition is that graph stability does not guarantee graph feasibility. And here's an example. So in the below images, we have a fetch robot trying to grasp the green chips bucket. All the graphs plotted using arrows are equally stable in these images. But the blue graphs are infeasible either due to out of range of self-collision. So only the red graphs are reachable, even though they are all equally stable. So we then introduced the idea of reachability space for each robot using a sign distance field. So for each 60 robot workspace, including the position and orientation, so we first compute a binary reachability space. So we densely sample graph poses in the workspace, then we check IK, and then we check self-collision. This is an example of the binary reachability space for the fetch robot. The green indicates reachable grasp, and the red indicates unreachable grasp. We then create a sign distance field from this binary reachability space, so that for each grasp in the binary space, we assign a continuous value. And the grasp on the boundary between reachable and unreachable has a value of 0. Negative value means unreachable, and positive value means reachable. And the magnitude of this value indicates the distance from the boundary. This is an example of the generated sign distance field for the fast robot. For example, let me use the laser point. Oh, can you guys see the cursor? The laser. Okay. So for example, for grasp around here, it will have a large negative value because it's far from the boundary and it's unreachable. And for grasp on the boundary between the red and green, it will have a value close to 0. Right. So after having this sign distance field, for those graphs that are not in the binary reachability space, we can just run multilinear interpolation to get their SDF value. So then we now have a function that takes in a grasp pose and returns a reachability value. The thing we need to notice here is this function runs pretty fast because we can generate the reachability space offline, and the reachability space for each robot is fixed. And then we can do online inference on the reachability space, which is pretty fast. And using this reachability function in static grasping improves the performance. So the typical grasp planning algorithm optimizes an objective function that is purely based on the grasp quality. But having this reachability function, we can modify the objective function to also include reachability components. And this has been proved to improve the performance. And in this project, we show that this can also help in dynamic environments. Firstly, computing this reachability is faster than computing IK. So we can use this as a filtering or ranking function to quickly rank all the graphs in our database and to select those graphs that are likely to be reachable. And this makes having a big graph database possible in real time. Secondly, reachability can be an indicator of manipulability. And our intuition for that is a graph with a high reachability value is more likely to remain reachable in the future as the object moves. So that will reduce the number of grasp switches as the object moves. So this is a visualization of the reachability value of all graphs in the database as the sugar box moves along the red trajectory. And as we can see that the reachable graph that is closer to the robot arm has a higher reachability value. Right. Feel free to ask any questions if there is any. So we have talked about the reachability awareness, and then the second interesting thing about our grasp planning algorithm is the motion awareness. And the observation for this is that the success rate of grasp depends on the motion of the object. This is an example. So here are two grasps on the pen, a side grasp and a top-down grasp. So if the pen is stable, if the pen does not move, both of the grasps are stable. But however, imagine on the left image that the pen is moving towards your palm. Let me do a live. Can you guys see me and the pen? So
yes, we can see you.
Yeah, so if the pen is like moving like this, the side grasp is more robust to such a motion, but a top-down grasp will likely to like miss the pen. I hope that makes sense.
Yes, despite the pen disappears into your background sometimes.
Oh, okay. But anyway, I have another illustration of this. So this video demonstrates the same idea, but using the Pi-Blue simulation. Every graph shown here are stable graphs if the object does not move. But as the object starts moving, some graphs fail and some graphs maintain a high success rate. And that's dependent on the object motion. Right. Hope that makes sense. So we define the motion-aware quality for graphs on an object to be the probability of success conditioned on the object motion. And furthermore, we define the object motion to be a moving direction denoted by theta, which is the moving direction, and a speed denoted by v. And the goal is to have a function that takes 60 graph poles, theta and v, and gives us the motion-aware quality.
Can I ask a question?
Sure.
When the object is moving and then it's grasped, does the object's motion then respond to the contacts of the grasping process, or is that object motion assumed fixed independent of the grasp?
So your question is, does the motion of the object is the motion of the object affected by the contact?
Yes.
I think so. So what we did is by having the object move following some trajectory, and then as long as there's contact happen, I think the object is totally affected. The trajectory is totally affected by the contact. It will change the original trajectory of the object. Does that make sense?
Yeah. When you're simulating in new Pi bullet,
yeah,
you simulate for some period of time this grasping action, I guess, and you have to decide on the basis of the simulation whether that grasp was successful or not as you're building up, right?
Yeah.
I guess there's two questions in there. How do you know when to stop simulating in Pi bullet? And are there non-physical artifacts from the simulation that might cause you to get incorrect conclusions about stability of grasp?
I see. So the first question is, when do we stop the simulation? We stop the simulation either the object is knocked down or the object is lifted up by the gripper.
So when you are sure about the success of the grasp, you stop the simulation.
Yes, when the object not necessarily a success, but as long as the object is lifted above the ground, we stop the simulation. But that doesn't mean it's a success. We have a threshold for the object to be above a certain height to define as a success.
Okay.
But we do stop the simulation if the object is knocked over or it's above, it's lifted up even just a little bit. And the second question is if there's any physical artifacts that affect the simulation that might not, that makes our simulation not as real world. I think there might be, but we try our best to like simulate the timing and also the force. So the way we move the object is by applying a constraint with a certain force to drag the object along the predefined trajectory. And we didn't, even though there's contact happens, we still keep applying the force. So we are hoping that will be more or less matching the real experiment. For example, on a conveyor belt. On a conveyor belt, there's this force dragging the object. Does that make sense?
Sure, that's fine. Thank you.
Yeah, sure. Thank you. Okay, so let's continue. We are trying to get a motion aware quality for the graph planning. So the most straightforward solution we can think of is to use machine learning. So we define a classification problem basically. 1 indicates success and 0 indicates failure. And then we collect a data set of 10K graphs, each on 7 objects. So for each of the data point, we sample a graph from our database, and we sample a moving direction, and we sample a speed. And then the simulator will execute the graph and label the data point as success or failure, right? So do you guys mind mute the microphone? Because sometimes I hear myself, if that's possible. Right. Thanks. Right. So after we collect this data set, we train with the modular perception network for 100 epochs, and we are able to achieve a validation accuracy of about 0.96 and a false positive rate of around 0.01 and a false negative rate of about 0.1. Then the raw output after the softmax layer indicates the probability of success, namely the motion aware quality given the current motion. So now we have another function that runs pretty fast. It takes the graph pose, the moving direction, and the speed, and gives us the motion aware quality. This video visualizes the motion aware quality of all graphs in the database. You can see that the quality value matches our intuition that graphs facing the direction of the motion have a higher value of motion aware quality. So now that we have introduced the 2 functions, the reachability function and the motion aware quality function, we will now present the final graph planning algorithm that uses these 2 functions as 2 ranking functions to quickly filter and then select graphs in our database in real time. So for each target object, given the graph database G sub DB of these 100 candidate graphs, we will include the top 5 graphs with the highest reachability and the top 5 graphs with highest motion aware quality into a filtered subset G sub F. And we will pick the graphs in G sub F that is closest to the current ARM configuration to be our final planned graph. That will make sure we have the least ARM motion. We also tried a bunch of other ways to combine these 2 ranking functions, including using a weighted combination of these 2 values. But experimentally, this method works the best in our experiment. So eventually, this video demonstrates the graph planning pipeline. And on the left, we plot the final selected graphs from our database. When a graph switch happens, we use a different color. On the right, we visualize the reachability and motion aware quality. Great. That's the graph planning algorithm. The second component is the object motion modeling. So now we will just briefly discuss the object motion modeling component. And this component is important because we need to understand the motion of the object so that we can predict a future pose of the object to plan a graph on. Otherwise, the robot arm is always trying to go to a graph plan using an obsolete pose, and then the robot arm will never catch up with the target object. So the motion modeling component in the project uses a recurrent neural network, specifically LSTM, and we generate the data set for the network by randomly sampling linear, circular, and sinusoidal sequence of waypoints, 2,000 each for each trajectory. So the input for this sequence, so the input is a sequence of object poses, and the output is the future pose. And to estimate the object poses in real time on the real robot, we use DOPE, which is method that takes in RGB images and return the estimated poses. And the third component of this project is the arm motion generation. When a good grass is planned, the arm needs to generate a collision-free motion to reach that collision-free grass configuration. And that's what the component does. And as we briefly talked before, a big challenge in arm motion generation in a dynamic environment is to be able to replan in real time. The traditional group of sampling-based methods, such as RT or PRM, is not well suited for continuous replanning because of their randomness. So on the right, I'm showing an 2D example of the RT planner, so that the green dot is trying to catch the red dot. And because of the randomness of this sampling-based method, as you can see, it's generating some wavy and a totally different solution from last time. That makes the green dot waste a lot of time as the target dot has already moved away. And this translates to the robot arm becomes jerky and wavy motion of the robot arm. And another group of methods for arm motion generation, the optimization-based methods such as chomp or stomp, they are also not that well suited for this problem, because even though they tend to give a more optimal solution that is more consistent across time, these methods are time-consuming to run compared to sampling-based methods. So our solution is to use RT with trajectory sampling so that we seed the random tree with the solution from last time. And this gives us two advantages. The first is we achieve temporal consistency in return path because of the seeding. And also because of the seeding, we can achieve some speed up in computation. Great. Now we have introduced the three components. We will talk about the simulation experiments of this project. We run simulation in the Pi-Blue simulation on 4 different methods. Ours is the method that includes the top 5 graphs using both the reachability and motion-aware quality ranking functions, which is the proposed method. The second one, reachability, only includes top 10 graphs using the reachability function. The third method, motion-aware, only uses top 10 graphs with top motion-aware qualities. And the baseline method just randomly pick 10 graphs from our 100 graphs database. Apart from this, we also run application study to research the importance of the other components. No trajectory seeding is a variant of ours, but without trajectory seeding, and similarly, no motion prediction is a variant of ours, but without motion prediction. We use 2 different robots, a Miko arm and a UR5 with robotic gripper to evaluate our system. And we sample 7 objects from the YCB dataset. These are the 7 objects. It's worth noting here that we can't go too crazy by selecting any object from the YCB dataset, because we have to consider the size of the object so that they fit into the robot hand. So that's the 7 objects that we end up choosing. And we evaluate our method on 5 different tasks: linear motion, circular motion, sinusoidal motion, and static obstacles, where we use the linear motion and we put some static obstacles randomly in the green rectangular region. And to further reduce the workspace of the robot, we simulate a top slab obstacle over the linear trajectory. For each object, we run 100 trials with randomized dl theta r. As shown in the bottom right image, d is the direction of the trajectory, l is the length of the trajectory, theta is the angle, and r is the distance of the trajectory to the arm, to robot arm base. And here's the result. And each number is reported over 700 trials, 100 trials for each object. There are a few things I want to highlight here. Firstly, the x-axis is the different task. The y-axis is the success rate over 700 trials. And on the left, we have the results for the Miko arm. And on the right, we have the result for the UR5 arm. And we compare the 4 different methods. So the first thing is ours, reachability or motion aware are always better than the baseline. And that makes sense because with these ranking functions, we can quickly focus on those graphs in our database that is either reachable or robust given the current robot motion. And the second thing is ours. So the red bar is almost always better than reachability only, the cyan bar, or the motion aware only, the green bar. That also makes sense because ours, by including the graphs with top values from both within both ranking functions, we have a wider range of good graphs to choose from. Right. Thirdly, we also noticed that reachability only. So the cyan bar is better than motion aware only, almost always better. What this tells us is that reachability awareness is more important than motion awareness in dynamic environments. This also matches our intuition because imagine a dynamic grasping task, even though a grasp that you pick is robust given the current object motion, if it's not reachable, then that's a waste of computation time. Like, for example, computing is IK, that's a waste of time doing that.
So Jingxi, if the replanning speed can be significantly increased, then this difference might disappear, I think.
Could you say again?
I mean, if the replanning speed for the motion aware only case can be improved dramatically, then its performance might be even better than reachability.
Yeah. Yeah, I think you're right. I mean, if checking IK doesn't take time at all, then I believe motion aware might have a smaller gap to reachability. I think you're right.
Yeah, my point is only to say, this observation is based on this setup, is not globally generalizable. Yeah.
But the thing is, it does take time, right?
Yes.
Yes. Checking IK, it does take time, and it's not like we are already using like one of the best IK solver, but in a dynamic environment, it still takes time to like check IK for all the graphs in a big database.
Yes. I think based on the current research situation, this is a good conclusion.
Yeah, definitely. Thanks. So, and
I have a quick question. Under what the previous slide, under what circumstances the reachability will be better than yours that combine both reachability and motion aware?
Right. That's a very interesting question, and we actually spend a lot of time thinking about this. I think So for the reachability method, we pick the top 10 graphs purely based on reachability. And for ours, the top 10 graphs consists of 5 most reachability one and 5 with
I see.
the top motion aware quality, right?
I see.
So, and then we pick the final graph using, we pick the final graph that is closest to the current arm motion. So if the final graph we pick is from the motion aware, is from the 5 graphs with highest motion aware quality, but turns out to be not reachable, then that's bad. So in this case, the reachability method might be able to solve it by feeding 10 graphs data with the highest reachability value. Yeah.
Okay.
Yeah, good question. Cool. So this is the second plot. The second plot that I want to show. And this plot compares ours with the application study.
Can I interrupt for a moment?
Sure, yeah.
So on the previous slide, is the performance trajectory dependent, or like, I mean, why? Or let me put it this way: is there any dependence between the success rate and the trajectory of the object?
I think so, and that's why we evaluate on different tasks. So on the as we can see on the x-axis is different trajectories, and there definitely is some difference between different tasks. And actually, we will see more results that is dependent on the task in the next slide.
Thank
I
you.
have a question on that too. Is success binary, either you completed or not, or is there some third dimension to that with, I don't know if practicality is the right word, but the cost function of time and speed and efficacy of the gripping versus just it worked?
Well, yeah, that's a good feedback. And actually, we report the grasping time in the paper, but here we just plot the success rate for like a better visualization. But in the paper, we does provide like grasping time as our another dimension to measure the success of different methods.
Conveyor belt, and you slowly sped the conveyor belt faster and faster and faster. Would that essentially account for how fast you can compute where the object is, and at a certain point it would fall off the end because you're no longer fast enough to keep up with the conveyor belt?
Yeah, so we did different experiments on different speed of the conveyor belt. So we moved object in different speeds. In general, like our system can handle up to like 5-6 centimeter per second speed. And if we go further beyond that speed, there's a big performance drop.
For us lay people, I think it'd be helpful if you compare that to, that's the speed of a moving walkway versus a bottling machine versus, you know, a UPS plant where they sort the packages to contextualize what that is physically.
Yeah, but the problem is for some of those warehouse applications, they do assume a known object motion. So that's the difference here, and it's hard to compare to like a pipeline that assumes the motion is known, like assumes the linear motion with a certain speed. But for ours, we don't assume any prior knowledge, and we even vary the speed during a single trial. Yeah. Does that make sense? Should I continue?
Yes.
Oh, okay.
Ming, you have the question?
Yeah, I have a quick question. Like,
I'm aware that this work is kind of reactive, like adaptive, right? Online. It makes sense, right? Like if you have initial motion planning and during this executions, you need to replan, right? And be reactive to the, so you need to replan, is that correct?
Yeah, that's
so
absolutely
so my question is, how's the robot aware that like if he needed to replan because of the incorrect prediction?
right. So we now use an aggressive approach so that we basically just keep replanning all the time. When the last replanning is finished, we start to use a new observation and keep planning again. But we do have some like little engineering tricks that, for example, initially when the robot arm is far away from the target object, we don't replan aggressively. We don't replan all the time. We only start the replanning when the robot arm is close enough to the target object. Yeah.
So if it's possible to use a model predict control to do that.
I'm not very familiar with model predictive control, but so I'm not very sure what you mean by that.
Okay, yeah.
But I'm happy to, like, if you want to discuss further about this, I'm happy to learn your feedback. Yeah. Okay. So shall I continue? Any more questions?
Please.
All right. So the second plot that I want to show is the ablation study. And there are two things I want to highlight from the ablation study. Firstly, we noticed that the seeding is really important for the top slab and the sinusoidal task. And this is because for the top slab case, the workspace of the robot is the most restricted, and if without seeding, it's going to take a long time to plan the motion, and the object target will move away. And for the sinusoidal task, the target object is jiggling around, and without seeding, you will have a drastically different path from last time step. This is not good, so that we see the biggest gap in these two tasks. The second thing is the prediction is very important. As we can see, without prediction, there is a very large performance gap. This is because without the prediction, the arm is always trying to move to an obsolete pose and will never catch up. Another thing we would like to highlight is that the UR5 suffers more from no prediction. As you can see, there's more performance drop on the right side. This is because the UR5 gripper is very narrow compared to the Vico gripper. So that means we need a very precise motion, approaching and grasping motion. And it's very hard to do that.
How many joints does the Vico have?
I think 6 degrees of freedom.
6, okay.
Yeah. Okay, so here are some qualitative examples of the ablation study. We compare ours versus no trajectory seeding. And without trajectory seeding, the arm is wavy a lot. The second video compares ours versus no prediction. Without prediction, the arm simply knocks down the object because it's trying to reach grass pen on the old pose. The last result I want to show is we further investigate the importance of reachability by varying the distance of the trajectory to the arm base using linear motion. And the x-axis is the distance, from the arm base, and the y-axis is the success rate. So the top chart shows Miko results, and the bottom chart is the UR5 results. As shown in the plot, reachability plays a more important role when the object is extremely close or extremely far away from the robot arm. Those areas are where the workspace is most restricted, and being reachability aware is able to alleviate the performance drop. Okay, here are some simulation demonstrations for the Miko arm, and some simulation demos for the UR5 arm for different tasks. And lastly, we briefly validate the algorithm on a conveyor belt on a real robot using the UR5.
Did you do physical experiments on the using the circular or sinusoidal trajectories?
Unfortunately, no. It's during the pandemic, and also it's hard to having a circular sinusoidal conveyor belt. It's hard to do that. Yeah. And that brings the end of the presentation. For more information, you can visit the website or the archive version of the paper. Yeah, thank you so much for your attention.
I have one other question, if I can.
Sure.
So you showed some videos of successful grasps, and you showed some animations of successful grasps, but you didn't show them side by side. Like, it'd be nice to see the prediction of a simulation successful grasp and the actual system successful grasp. Do you have plans to try to show them side by side?
Could you say again to show what two components side by side?
At the end, you showed simulation of successful grasps, right? And you also showed real world experiments of successful grasps.
Yeah.
I was trying to remember from the videos from the simulation if any of those were almost identical to the real ones. It would be nice to see them side by side to see the differences.
Interesting. We haven't got to that point yet, but I think if we have enough time, it might be interesting to compare these two side by side.
Or just gazebo or something, or whatever the planning software is, and have screen capture of the computer. That's what the computer's trying to do and what it actually did, if I'm understanding. Like, I think you have the data, you just have to capture your computer while you do it.
Yeah. It's hard to connect the Pi simulator with the real robot video because it's not guaranteed to be the same, and they are not connected. But we might be able to show some RV's visualization of the planning for the
that's part of my point, and part of getting back to what I was asking earlier in your presentation about the reality gap. So, we all have to deal with simulations. They're never perfect, and the question is, are they good enough? And where they're not good enough, how do we change our system to adapt, or how do we change our planning method to adapt to that difference?
I think that's a good point. We haven't got to that point yet.
Yeah, thanks.
Yeah, thank you.
I have one question if we have time.
Sure.
Okay, so you mentioned the motion aware grasp quality metric, which takes the grasp pose, the object speed and direction, and that helps us differentiate between, let's say, side grasps and top grasps when the object is moving sideways. Can this function also differentiate between two side grasps, in which in one of them where the object is moving away from the arm or from the gripper, and in the other one where the object is moving towards the arm. Could the function differentiate between those graphs?
Yeah, I think so. Yeah.
Could this also eliminate the need for a object motion modeling or object motion prediction by favoring the graphs where the object is always moving towards the arm?
Yeah, so here are two questions. The first question is, does it differentiate between two side graphs? And the answer is yes. I think you are absolutely right. If it's even we have two side graphs that are equally stable, if the object is static, those facing the direction will be more favored. That's right. A side graph from behind the motion is likely to be less favored. Then the second question is, does this eliminate the need for motion prediction? The answer is to some extent, like it makes it more robust if you don't have a perfect motion prediction, but I don't think it's able to like fully eliminate the motion prediction part. Yeah.
So one last question. What is the control of this robot? Did you do just position control or velocity control?
I think in the simulation we did position control, and in the real hardware, I'm not exactly sure. I can ask for you because I didn't do the real robot experiments.
Okay, the reason I'm asking is because if it's only position control, then you can't, when you are approaching the object, you are relying on the replanning to adjust its position at each time step. But if you can also you can use velocity control, then in the planning you can try to make the robot and the effector moving along with the object. Then when your gripper is approaching from different directions, if the velocity of the object is compensated, then the success rate will be improved a lot.
I see. That's interesting. We haven't thought about that, like the velocity control. We did think about like matching the speed of the robot arm and the object, but that didn't go too far.
Yeah, you will need velocity control.
Yeah, good point.
Can you explain more about the trajectory seeding procedure? Like, because for each peak, you have different start and goal. So how does it work?
Could you say again? For each
peak, you have different start state and different goal. So how does that work? Like you use you're seeding, like you're replanning based on the previous trajectory.
Yeah.
So how does that?
Yeah. So when you have a new starting location, the easiest way is to simply connect the new location to the closest configuration on the existing tree. That will work most of the time because these two are close and it's likely to be collision free to just connect these two. And then starting the planning with this new tree. Yeah.
So how about the goal? I mean, when you're reaching the goal, the state could be like very different from the previous one.
So, I think that's just the job of the RT. You don't need to connect the goal to the tree. Even for RT, the goal is not connected to the tree until the tree is expanded enough. So we just use the existing. We just expand on the existing tree until the new goal is reached.
Okay.
I hope that answers your question.
Okay, thanks.
Right.
Okay, if there's no more questions, let's thank Jingxi again.
Thanks.
Okay, so thank you, Jingxi, and in the future, we when the pandemic has ended, we are, if it's possible to visit our campus, we can, show you around.
Sure. Yeah. Hopefully, I will have some more work for my PhD. So
yeah, and hopefully you can join us, with our famous gyro lunch.
Sure. Yeah, I love to.
Okay.
Thank you.
All right. So, okay, thank you all.
Yeah. See you all.
Yeah, have a good weekend. Bye.
Yeah.